Hello all and welcome back to this decision analysis lecture notes, video lectures. And now we are in chapter 4, final section, section 4, about visualizing sensitivity. And we have a Sheldon Shore here as an example. And the idea here is that in many cases, the data, you cannot estimate certain parameters, or certain parameters are free to be chosen. So we take two parameters that are so-called free. They are called sensitivity parameters, and then we make a picture that shows what is the optimal decision once these parameters change. So that's the idea. And in chapter 7 and 8, when there are your assignments given and the related examples in chapter 5 and 6, the idea is that you always have two sensitivity parameters. So this section is about visualizing given sensitivity parameters. So pay attention. This helps you a lot in doing your assignment if you understand what's going on here. And in this example, in this section, we first encounter our disease called koala Ebola. It's an infectious disease that may evolve into a global pandemic or not. We don't know it. So the idea is that so far the koala Ebola has only been encountered in Australia, but unfortunately Australia is a popular tourist attraction and the koala Ebola has penetrated the entire land. And Australia has not enforced any kind of quarantine yet, so it may be just a matter of time that we have global pandemic at our hand. So this is the backdrop or the backstory. So what is our problem? We have a Sheldon share that has 100,000 euros extra money to invest, and Sheldon does not believe in diversification, so instead he will put all his eggs in one basket, which is probably not a good idea, but this is our setting anyway. And there are four different investment possibilities for Sheldon share. So A1 is to invest in retail company stock, and then a bit more bold, A2 invest in retail company call options, so using financial derivatives here. Then A3 invest in an airline company stock, and A4 more boldly invest in an airline company call options. So these are the alternatives, four of them, and no diversification. Instead, Sheldon will use one of these investments. So then what are the scenarios that Sheldon thinks that are relevant to his choice? So there are three scenarios. S1 is koala Ebola runs rampant, so we have a pandemic at our hand. S2, koala Ebola is contained, but the economy is in recess. And S3, koala Ebola is contained, but the economy is booming. So these three scenarios, one of them will occur. And now comes the first time we encounter a sensitivity parameter. So Sheldon assumes the probability of these scenarios would be P1, so this koala Ebola runs rampant, so we have a pandemic probability. That's P0. P0 is just, we don't know what it is. It will be a sensitivity parameters. And then P2 and P3 are equally probable, so the probable are Q0. And because of this setting, so P0 plus Q0 must be 1, so we immediately see that Q0 is actually 1 minus P0 over 2. So we see that Q0 is not a free parameter, it's determined by P0. And why are these P2 and P3 equally probable? So, well, this is the so-called maximum entropy principle, meaning that we have no reason to assume that the probabilities are different in any special way, so we assume them to be the same. So this is just the principle. And also recall that P0 is not fixed, it's a sensitivity parameter. So next we have to find the reward or decision matrix for Sheldon share. So Sheldon has consulted best investing experts, whoever they may be, and they have given the following decision matrix. And the values are here returns. So this is the matrix. So A1 with S1 is 80% return, with S2 is minus 50% return, and with S3 10% return, and so on. So whether these are reasonable or not, that's a good question. So we have to rely on experts, and experts say that these will be the returns in different scenarios. And then Sheldon has to decide how will he react to uncertainty. So Sheldon will be a risk-averse person with a constant absolute risk aversion utility. So this is utility function u of r is 1 minus e to the power minus r over r0, where r0 is the risk tolerance. And again, unfortunately, Sheldon does not know what is his risk tolerance, so this r2 will be a free sensitivity parameter. So now we have two free sensitivity parameters in our system, p0 or p0, that is the probability of the pandemic, and then another one we have the risk tolerance r0. So p0 is from 0 to 1, and r0 or r0 is a positive number. Then a minor but important remark. So because Sheldon shall use the utility rule, it means that you should not calculate with returns. So returns are not the reward matrix, but with outcomes. So therefore the decision matrix will be from this, you get the outcomes here, where C is the amount of money to be invested. So 80% return means that your capital of C will turn to 1.8 times C. Here minus 1% return means that everything is lost, so you will get 0. 400% return means that it's 5 times the original amount, so 5.0 times C. So this is essentially this matrix, but not with returns, but with actual outcomes, actual money earned from investment of C 100,000. So because the utility rule, it has to be used. This because the utility rule is not linear, so this transformation here will give different results than if you use this returns as such. So utilities should not be used for returns, but actual outcomes. All right, so let's then solve the Sheldon's problem. So Sheldon has two parameters, P0 and R0, and he does not want to estimate them. Instead, he treats them as sensitivity parameters and plots the outcome for different returns. And this is what happens in this file example shsh.m. And again, let us, from here, we download this. Let's see if everything works. It was a bit slow, but yes, it downloaded it. So let us look at our down directory, downloads directory. And now we have downloaded these 6 M files. So these 6 M files should be in your working directory for Octave. So now you should, this is the newest one, example underscore shsh. You should copy or move this to the Octave working directory. So again, let's look at through the code, what it does, and then try to analyze the results. So I open again Octave, so this kind of icon. My computer is slow today for some reason. All right, then I change to the directory. So for me it's work, teaching, ORMs 2020, N. Yours may be different. And I look at, so example SHSH should be there. It's like this, it is there, good. So let's first just run it to see if it works and what does it do. So example SHSH, just type the name of the M file. Now it takes some time because it will generate a big matrix and then a picture from this matrix. So we have to be a bit patient. Still calculating. Calculating. And now it's finished, and it gave us this kind of picture. So what is this interpretation of the picture? So we have P naught here in x-axis and R naught in the y-axis. So if P0, the corona, sorry, koala Ebola probability is 0, then we are here, and if it's certain, then we are here. And these are A1, A2, A3, and A4 are the choices. So you can see that if, for example, the risk tolerance is very small, so Sheldon share is very risk averse, then A1, which was the retail company stock, is almost always the choice. And then the more the risk tolerance, the more even the choices will be with respect to P naught, that is the koala Ebola probability. So for example, if the risk tolerance is high and Sheldon share does not believe that the koala Ebola will not turn into a pandemic, then A4 is the best choice. So the solution of this problem is this picture, and it's an interpretation of this picture. So with what is the optimal choice with different values of P naught and R naught, and then if you believe, then you have to believe that you are in one point here in the picture, and then choose that one. All right, let me close this window and let's go to the editor and open this example shss.m. Control plus makes the font bigger, and let's go through this code so to understand what's going on. So first we have a rather long comment block which starts with file example shsh.m, which is this name of the file, and then what happens next is this is just explanation of the problem. So I have copied from the lecture notes what's going on here, so let's not go through this again. This is just here for convenience to the reader, so the reader will know what this file does. And let's then go to the code. So first block we have calculations and definitions for the visualization. So we have a reward matrix. So C is the money to be invested, that's 100,000, semicolon always at the end, so we don't want it to print it down. Then the reward matrix, this is now in terms of C, so it's here, this is the lecture notes. And what comes next? Next comes, we have to solve these decision problems for different parameters. So I decided capital N to be the so-called sampling frequency for P naught and R naught. So the idea is the bigger the N, the better the picture. So the picture is smoother and more precise, but the longer the calculations take. And I've just put here, for example, in my computers, the N is 100, the calculations take 1.5 seconds, and if N is 500, the calculations will take 35 seconds. And now, for the purpose of this demonstration, I take N to be very relatively small number, 10. So we don't have to wait when we test this function, and we see how the picture changes. So I take a sampling frequency N, so N equal 10, so then R0 samples, sorry, this is P0 samples, so these are samples for P0. So there is this octave function linspace 0, 1, N. What does it mean? Well, I show you linspace from 0 to 1, say 5, for example, is like this. It takes values from 0 to 1 so that there are 5 values So then it means that first is 0, then it's 0.25, 0.5, 0.75, 1. For example, 6 values is like this, 0.2, 0.0, 0.2, 0.4, 0.6, 0.8, and 1. All right. So the lint space here takes values from 0 to 1, n values. So P0 samples are the values for P0 that are numbers between 0 and 1, and there are n of them. The same thing for R0 samples. R0 is the risk tolerance, so the risk tolerance values are positive numbers, so I take lint space from 1 to 10 times C, which is 1 to million. So the risk tolerance is, we check the risk tolerance is between value 1 and million, and we take also n of them. So for example, lint space 1 to million is that million, and 6 values is like that. That's 100,000, sorry, let's take a million. All right, so 0, 200,000, 400,000, 600,000, 800,000, and 1 million. All right, then we consider the decision problem, and first we look at there are some constant fields. By constant fields I mean the fields that don't depend on P0 or R0, so we can set them here before going to a for loops. So dp.dmat, so dp is the decision problem, field dmat, decision matrix, this will be the R, capital R, that's here. Then the next is the decision rule, so dp.drule, this is fixed, it's cara. I note that there are small caras, maybe I should have used capitalized here, but it's defined so that it's small letters cara, constant absolute risk aversion, and in the quotation marks because it's string. Again, note the semicolons there. And what happens next? And now this is the complicated stuff, but this is what we will observe this kind of system in many of our examples, especially the assignment examples that are to prepare for your assignments. So I have two inner for loops, and the running index is I and j, and what I do there is set ji. So Z will be a matrix with row j, and column I will be the decision result d-optim. So this will be a matrix where there are for different I and j's, they are the optimal values of the decision problem, or the d-optims or decision result. So let's see how this works. So I have outer for loop for I goes 1 to n, and x, so this will be the x-axis, will be P0 samples at point I. So this will be the P0. I could have denoted x as P0 and later I do it so, but here it's just x. And then the decision problem, its probabilities will be x, 1 minus x over 2 and 1 minus x over 2. So this was P0, Q0, Q0. And again, this is a column vector, so this is the single quote there. Remember that it doesn't work if you forget this little quote mark. Again, everything ends with a semicolon. So this is for each P0 samples, x will be the probabilities, and decision problem will be with these probabilities. So this is a varying field. This probability depends on I, or P0 samples at point I to be more precise. Then we change the same thing, but now j. So this is the y-axis. It goes 1 to n also, and y will be the R0 samples at j. So this will set the risk tolerances from this vector R0 samples at this linear space from 1 to 10 times 100,000 and with n different values. And the same thing now, decision problems RTOL, risk tolerance will be Y. And now we have a decision problem set. So we have the constant fields here, dp.dmat is R, dp.drule is Kara, dp.prop is this, and dp risk tolerance is Y. And now we can solve this dpd problem. So dr is the d matrix dp, that's the solution, and this is put in the matrix Z. And know that the I and J are now in the wrong way around, because matrices you have rows and columns, and in a picture you have x and y axis, and they go the other way. The direction is rotated 90 degrees basically. So this is just an artifact that you have to have Ji here. And what this will be the dr, the decision result, and the d-opt. So now it means that the Z contains the values, the optimal decisions for this D problem when X and Y that are P0 and Y is R0 when they change. And at this point I have 10 is the value of the samples. So let's try calling this now. So I remove all the variables that I have. And now we run it very fast. There is a picture which doesn't look completely correct. It has this kind of, I could call this artifacts, this kind of, it's not smooth but goes like this. This is because the sampling frequency is low. Let's not worry about this yet. Let's just look at the Z. So this is the matrix that tells the optimal decisions. And here this is the R0 is small here and increases. So this is this here. Let me get back the picture. So it has to be understood that this corner here is this corner here, and this row here is this row here, and this, for example, this row here corresponds to this row here. So it's flipped. The y-axis is flipped in the Z when this is the rows and columns, and these are the x-axis and y-axis, or p0 axis and r0 axis to be precise. Nevertheless, so now we have this Z, and then the question is how from Z, this matrix, we get this picture. So this is what happens next in the code, and this is the plotting of the sensitivity picture. And this is something that it's very easy to have some kind of plot, but then we want to have the plot to look nice, so then there's a lot of other things we have to say. But in principle, this is what does the plot. So contour F, it means contour F here means field. So it's a contour plot where x-axis X is P0 samples, these are the X values, R0 samples are the Y values, and then Z is what is to be plotted. So this does the plotting. I could only have this, but then the plotting would be not very nice. So then I fine tune a little bit. So this kind of strange looking construct, look at the axis. So I set the value. GCA means get current axis. So we are looking at the current axis of a picture. So current picture is this. And then I have a variable font size, and I put it 22. So the x-axis and y-axis labels will be now bigger font. Font is 22 points. And then x label, this is what will be there, P0, and y label R0. So that they are there so that we get this here, this P0 and this R0. They were produced by these. Then we have the colors of the picture. So if I don't give anything, it uses standard colors, which I find ugly. So I define new colors. So colors can be defined by RGB coding. So it's a vector where it's R value, red value, green value, and blue value. So I called red, which is red value full and no green or blue. And then there's a green value, which 0 red, 100% green, and 0% blue. So these are just the definitions of colors in RGB coded. And then color map, this will change the colors of the picture. So this is a matrix that has rows of colors, and then when it draws the colors, it will start using first color this, then second color this, then this color, this color. So I will have red, 0.5 red, this will be dark red, then green, and 0.5 green, so this will be dark green. So these are the colors here. So the first color is red, it's this, then second color is this, that's dark red, then there is green, it's this color, and then finally dark green, it's this color. And then finally in this picture I have to put these labels, also text X, A1, A2, A3 and A4 there, and this happens here. So text X position, Y position, what is there to be written, so A underscore 4, which is, it understands A subindex 4, and then with the font size 24. So this row here plots this. So how did I figure out which area is which decision? So there I use this matrix Z. So I just look manually that here it's 4, here it's 3, here it's 1, and here it's 2. And I picked here the X and Y positions manually like this. And that's it. So finally there is, if I want to print this to a PDF file, I can uncomment this. So I will orient landscape PDF and print children picture PDF. So this works for me. I think some Octave versions have problems with this PDF driver, so it doesn't work. So instead of using PDF, you can use, for example, JPEG or GIF. And also you can omit this and simply have this here, and it should save as, should work. So here it gives your Octave figure, which is probably not what you want, but then this PDF, let's hope it works. I'm completely sure. If it doesn't work, then the next best choice is probably JPEG. All right. And then finally, let's get back to this. So this picture is not correct. It's a bit an artifact because the matrix Z is too small. To make the Z bigger, then these borders will be more correct. And let's have this back to 500. This will take some time. Sorry about that. So Control S, I saved it. And let's call this, and let's time it now. Tick tock gives us time. Tick starts a clock, and tock stops the clock and prints how long has passed. So let's now check how long it will take for this big Z matrix to be calculated and then plotted. The plotting doesn't take time. The calculation of the matrix takes time because we are solving n times n squared different decision problems. So it obviously takes some time to do it. Now 45 seconds. Okay, so my computer is getting slower probably. So here you have, and now you can save it and include it in your Word document or whatever you are using. when you when you do your assignments. All right, so that was it. So then it's finally just the interpretation of the picture is obvious. So for example, in case of extreme risk aversion, R0 near zero risk tolerance, the optimal alternative is alternative A1, and as risk tolerance increases, all the alternatives become more or less equally optimal, depending on the koala Ebola probability P0. That was all for chapter 4. See you in next video lectures. Bye.